Just as in the case of the inverse function theorem, we're going to use the real analysis implicit function theorem to prove the implicit function theorem for analytic functions. So let's review that. This shouldn't be a big surprise because the implicit function theorem and the inverse function theorem are essentially equivalent because you can go back and forth between them through a standard trick. Nevertheless, this will tell us how to build certain analytic functions that satisfy a given equation. So for the real analysis implicit function theorem, we start with, let's say, an open set in Rd and an open set in Rn, and we'll have a function on u cross v into Rn that's C1, so it has all of its first partial derivatives exist and are continuous. And we need to label the variables of f, so the variables coming from u will be labeled with x underscore, and the variables coming from v will be called y. So I've labeled them here. X is x1 to xd, y is y1 to yn, and so on. And we're going to suppose that the derivatives with respect to the y variables give you an invertible matrix for some fixed AB in our product set here. And when you have this, you can show that the level set of f at the point AB, so this would be looking at f of x, y that are equal to this value at AB, you can show that the level set is locally given as the graph of a C1 function. So the conclusion is that there exists an R and a C1 function f defined on the ball of radius r centered at the point A here. And it maps from u into v, and it's going to be the function that we're going to take the graph of. So what our conclusion is that if you look at all points x, y on this level set, these are all points of the graph of little f. So these will all be points of the form x, f of x, where x is in this ball of radius r centered at A. So the big upshot is that level sets are locally graphs. And so you can solve for the y variables in terms of the x variables. And that way you get functions that satisfy equations, and they'll be C1s. You can take their derivatives and everything. Now, hopefully you've seen the implicit function theorem in a real analysis course before. Nevertheless, no matter how many times you see it, it can be a little hard to remember which variables go where and how this all works. So here's just a brief box about how I remember some of the implicit function theorem. This has to work when f is linear. So you could think of f here as this kind of rectangular matrix. It would be n by d plus n. So it would have a block here, A, which is n by d, and then a square block, which is n by n. And we would have vectors x, y mapping to a vector z. And this, since we've written it in block form, we can expand it as ax plus by equals z. And now if this were our function that's linear, we can solve for y in terms of x on a given level set. So that would be where z is equal to a fixed value c. We can solve for y in this if b is invertible. Because if b is invertible, I would start with this equation. I'd multiply both sides by b inverse and get b inverse ax plus y is identically equal to b inverse c. And then we get that y is given by b inverse c minus ax. So y is given as a function of x here. So whichever block in this rectangular matrix is the invertible piece, that's the piece where on level sets you can solve for those variables in terms of the other variables. Okay, and we have a note similar to what we had with the inverse function theorem that you can relate the derivatives of all of these functions. So by the multivariable chain rule, f of x lives on a level set of capital F. So this will be a constant, and maybe I should have just wrote constant here. And so when I take its derivative matrix with respect to x, this side will be the zero matrix. And then on this side, you can apply the multivariable chain rule. So you'll get the derivative matrix of capital F with respect to its x variables. And then this will be evaluated at x f of x. Writing all the details gets to be a little complicated, but hiding them also makes it confusing too. So we'll have the derivative with respect to the x variables plus the derivative of capital F with respect to its y variables times the derivative matrix of little f inside here. And so it only has x as variables, so I could write it there. And then from here, you can solve for the derivative matrix of little f to be expressed in terms of the derivative matrices of big F. And now what we're going to do is look at analytic functions. So if capital F is going to be a vectorized version of an analytic function of two complex variables, then these derivative matrices will be conformal, and so will this inverse matrix, and the product of conformal matrices will be conformal, and so the derivative matrix here will be conformal, and so the corresponding function of complex variables will be analytic by the Cauchy-Riemann equations. So this is just a straightforward conversion, but the theorem is huge. Let's see. So just writing down the theorem is the hardest part, but here is the implicit function theorem for analytic functions. Let u1, u2 be domains in the plane, and I'll have capital F a function on the product of those domains. And we're going to write out the variables of capital F as z and w. And we're going to assume that capital F is analytic in each variable separately. So z maps to f of zw is analytic for fixed w, w maps to f of zw is analytic for fixed z. And also, as in the implicit function theorem, we need a partial complex derivative to be non-zero. Then the conclusion is that there will exist a disk around z0 that sits inside u1, and an analytic function that maps u1 into u2 locally, so that the level set given by capital F at z0, w0 is given by the graph of this function little f, where z's are restricted to some small neighborhood of z0. So again, level sets are locally graphs, but now there are graphs of analytic functions. So we've built analytic functions that satisfy a given relation or a given equation. Capital F of z comma f of z is equal to some constant. So I've already said the proof out loud, but by the note over here, you can show that little f satisfies the Cauchy-Riemann equations, and so it has to be analytic by a previous theorem. Now let's look at a brief example of this. Here's a really basic example of the implicit function theorem, which is really no different than the inverse function theorem for analytic functions here, but it's good to see how they connect a little bit. So let's look at w squared minus z equals 0. So here our function capital F is going to be the function on the left. And so the partial of this function with respect to w just gives me 2w. And so the implicit function theorem will apply near any w naught that's not 0. And so I'm interested in kind of finding an analytic solution for this equation, meaning I want to find an analytic function of z in place of w. So if I'm at w equals w naught, then z has to be w naught squared. And so the implicit function theorem will give me w as a function of z, so there'll exist a function f defined around w naught squared, mapping to a neighborhood of w naught that satisfies the given equation, so lives on a level set of capital F. And so little f squared will equal z. And so this will be a branch of the square root of z at w naught squared, which we already know that we can do. And it's not too hard to show that you cannot do this at 0, 0, namely, well, the big reason is the implicit function theorem doesn't apply, but you could attempt it or ask, is it even possible? But if you had an analytic function that satisfied the above equation, it would have to vanish at 0, so it would have to start out at something like a1z, a2, z squared, and so on. And so you could factor a z out of it, z times some power series. And then if we satisfied the equation above near 0, you'd have a problem because you'd have a factor of z squared here equals z. So if you canceled those, you'd have g of z squared equals 1. And if you plug in 0, you get a contradiction. So you can't solve this equation near the bad point 0. Now let's look at another example. So here's a polynomial in 2 variables. And we want to show that you can find solutions to this as a function of z. So we want to find w as a function of z. And it turns out if you avoid certain points, the roots of this polynomial in w are given by analytic functions. So the partial with respect to w of the left-hand side here just gives me this. And so the implicit function theorem will apply whenever this expression is non-zero. So for example, if z and w are 1, this is non-zero, and I'm on the level set above, because if you plug in 1 in for z and 1 in for w, you do indeed get 0. So the implicit function theorem will say there exists an f mapping a neighborhood of 1 to a neighborhood of 1 that satisfies the given equation. So we have an analytic function that gives us the roots of this polynomial that you would view as having coefficients of polynomials in z. So you could use this to actually compute the power series at 1. I don't know that we have anything as nice as the Lagrange inversion formula in this case. One thing we can do that's a little different from the first example is look at the bad point 0, 0. So 0, 0 is on the level set in question, but at 0, 0, this partial derivative is 0. And in the first example, it's hopeless at the bad point. But in this case, you actually get that the 0 set kind of breaks up into 2 analytic graphs. And you can see that in this case by just solving, because you have this equation here is the same as the one I started with after rearranging. And you can just use the quadratic formula for w, and if you use the quadratic formula, you get this. And if you choose a branch of square root around 1, you'll get an analytic function w that satisfies the equation, but you get 2 of them because I have 2 choices for the branch. So both of these choices of branch here will give us a function that satisfies the equation, and they'll be distinct, and they'll both be analytic. And so this shows that all hope is not lost. It's just sometimes the zero set will break up into two analytic pieces, and sometimes it can't be broken up into it. And we'll learn later that there's something you can do in the situation where you can't break it up so easily, called Puiseux series. But this is just a basic example to show that we can construct these analytic functions satisfying polynomial equations directly from the implicit function theorem.